And so the goal for today is to answer some Tannakian questions. I think maybe the theme from today was joint work with Kevin Coulombier. So again, this is joint work with Kevin. And the main question we want to answer today is, when is a category, a tensor category, sheaves on some stack, where stack, of course, comes with some conditions. And this here is Deligne, and a lot of this work is based on classical work by Deligne. Okay. So the first bit will be a little bit of repetition. That Kevin already talked a little bit about this, as well as Alexandra. So we're going to start with a field, an algebraically closed field, to keep it easy. And let's take some affine group scheme, G over the field. Of course, we can think of this group scheme as a functor. And in fact, I like to think of it as a representable functor, which is represented, of course, by the group algebra. Or the coordinate ring. Okay, so if we consider the category of representations of G, for now I'll just stick to the finite dimensional representations. Then what do we know? We know it's abelian. We know that it's symmetric monoidal. We know that the endomorphism ring of 1 is a field K. And we know that all the objects are dualizable. And as has been defined already by Kevin today, we call such a category a tensor category. Okay, so this gives us a functor from affine group schemes to tensor categories. And it's not so hard to show that that is actually an embedding. And so it's a very natural question to ask what the image is. And we've already heard the answer today. We learned that there's always this forgetful functor to vector spaces. And you can show this faithful, exact, and that it respects the symmetric monoidal structure. In particular, we call such a functor a fiber functor. So we know that there is always such a fiber functor. And then we can call a category that has such a fiber functor to the category of vector spaces Tannakian. And if we do that, then you can in fact show that the image is exactly the Tannakian categories. So these two categories here are equivalent. This was first shown by Saavedra Ivano, but there was a little mistake, which was fixed by Deligne. Okay. You can also ask a different question, because Deligne wasn't entirely happy with this. So yes, this allows us to recognize the affine group schemes in here, but it appeals to some outside information, namely some fiber functor.
But when we say equivalent, this is not really categories. This is just a set of equivalence classes, yes? Because when you have a Tannakian category, it gives you a group scheme up to conjugation.
Okay, depends, but yeah.
But I think every Tannakian tensor functor though is still represented by Tannakian group schemes or something.
That's right, but
this is definitely
defined up to conjugation.
Sure, yeah.
Okay. Okay, so you can ask then, can I give an internal description that doesn't appeal to any outside information? And that is often called the description question. So we want to use intrinsic properties only for the category. This was done by Deligne in characteristic 0. So again, we saw this already today. C is rep G. Here C is some tensor category if some high enough exterior power disappears. And so now we have recognition and we have description. But then there's a third natural question, is given some Tannakian category in here, can I reconstruct the affine group scheme So if I have some fiber functor to K vector spaces, how can we build the affine group scheme out of it? So given some K algebra R, we can extend scalars to R modules. And that gives us a new functor. So first we apply W, and then we extend scalars. This is a functor. And then we can look at the automorphisms of that functor, the automorphisms that respect to tensor structure. So this is, and this will give us a group. So in particular, we get a functor from K algebras to group schemes. If we call this functor G, you can show that actually this is an affine group scheme. And in fact, C is equivalent to rep G. Okay. A different way of thinking about this is to actually, instead of thinking of it as an affine group scheme, we want to think of it as a representable functor. We want to know what it's represented by. And so a different way of approaching reconstruction is to actually try and construct KG. And let's do that. So for every object, we can apply the fiber functor. We can also apply it to its dual, look at the tensor product, and then do that for all x. And then there is something called a coherent construction, which if you've never seen this before, it is a type of colimit. So we take some kind of weird colimit for all x over these objects. So this will be some object in K-vec. And then you can show that this actually has a Hopf algebra structure and that we can recover RC as comodules over Kg. Okay. So before I generalize this, let's very quickly do two examples. So if we start off with a topological group, say over C, we can look at the continuous representations of the group of a C. And of course, we can forget the action. So we get a forgetful functor to C modules. And it's not hard to show that this is a fiber functor. But so by Deligne's theorem, we know that there exists some affine group scheme, G, so that the representations of G is exactly the continuous representations of Y. Okay, and so this G is often called the algebraic envelope of the topological group Y. So if you prefer doing just algebra over topology, you can replace it. But of course, G might be a lot more complicated than Y. Okay. Second example, again, something we've seen already. If you start off with some affine group scheme, we can do something called a semi-simplification. So what we're doing is we're modding out the ideal of negligent morphisms. And doing this, of course, we know that in C, C is certainly Tannakian, and we know that high enough exterior powers of every object in rep G disappear. So there exists an N such that for all x in rep G, we know that high enough powers, exterior powers of x disappear, so that this should be here. if we're working in the quotient, we know that this will hold as well in C. Because of course, if things already disappear in rep G, they should disappear in C. Okay. Let's move this. Okay. So by Deligne's theorem, we know that in characteristic 0, we can conclude that, in fact, C is Tannakian. So there should exist some G hat with rep G equal to a simplification of rep G. And so in representation theoretic terms, this will be the pro-reductive envelope of the G that you started off with. Again, might be a lot more complicated than the G you started with. However,
in the curve 0, are there negligible morphisms? I'm so used to that happening because I'm counting with B and then I'm getting 0 or something like this.
That's right, yeah. So, I mean, if G is not reductive,
yeah,
you might get, it will not be semi-simple, right? So, and in characteristic P, we already today saw an example where this fails. For instance, we learned that in characteristic P, we have the Verlinde category, which is rep CP, semi-simplified, and we already saw that this is not Tannakian. In fact, it's incompressible. So this tells us we definitely can't transfer Deligne's theorem to characteristic P because we have a counterexample. So we need new techniques. And the new idea came from Kevin Coulombier, who considered this composition. So given a tensor category, we can look at symmetric powers of the objects and also of divided powers. And of course, in characteristic 0, symmetric group representation theory is going to be semi-simple, and these two things will be the same. But in characteristic P, this might not be an isomorphism. And so, in fact, we can look at the image of this functor, and this is what Kevin called the jth Frobenius power. So if we do this construction where in C the category of vector spaces, then we just get the traditional Frobenius twist, hence the name. And Kevin's theorem was that some new version of the Deligne's theorem saying that not only do we need high enough exterior powers to disappear for C to be Tannakian, but we also need some new condition, namely if for some J, the jth Frobenius, or the kth exterior power of the jth Frobenius power disappears, then the kth exterior power already disappeared. So this construction looks kind of random, but it's not hard to see that this will be true in vector spaces, and a fiber functor will preserve it. So it should definitely be true if your category is Tannakian, and you can show that this will not always be true. For instance, it will fail in the Verlinde category already. Yeah.
Question.
Yeah.
So here, tensor means Tannakian.
Sorry?
Tensor means Tannakian again, like objects have finite length.
That's right, yeah. But that will change soon. Yeah. Okay. So what do we have so far? So we talked about how if you have an affine group scheme, you can look at the category of G which is a tensor category in the linear sense. But now we are going to embed it in the category of all representations. And we talked about Tannakian reconstruction, namely, given rep G, we can reconstruct the affine group scheme. Now, if instead you start with a scheme, some nice enough scheme X, we can look at the category of quasi-coherent sheaves on that scheme. And again, this is also an abelian category with a symmetric monoidal structure that in many ways behaves the same way as this category here. And so you can ask, can I reconstruct my scheme X? And the answer is if the scheme is nice enough, yes, you can. And that's called Gabriel-Rosenberg reconstruction. So we have this kind of short summary here for different reconstruction theorems. And so the idea today is, can I bring all of these constructions together? So let's think about these here. So certainly, not everything here is rigid anymore. Not all objects are dualizable. And here, the anamorphisms of the unit will no longer be a field. Right? So we need to broaden our idea of what a tensor category is. I'm going to call these Grothendieck tensor categories, and I'll define soon what they are. And the new function that I'm going to look at is, on the left, I want to have some algebro-geometric objects, which, again, I will make more precise soon. On the right, I'm going to have Grothendieck tensor categories. And I'm going to send an algebro-geometric object to the category of quasi-coherent sheaves on it. The functors, or the morphisms that I'm considering here are going to be left adjoints. So there will be functors that respect coproducts. And I'm going to send, if I have, say, a map between schemes, I'm going to take F upper star. Okay. Okay. So let's look at the right-hand side, Grothendieck tensor categories, and define what they are. So say if we start with a scheme and we look at quasi-coherent sheaves on it, we certainly have that is an abelian category. In fact, it's a Grothendieck category. So it's has coproducts and it satisfies certain axioms. So it's going to be a Grothendieck category. It's also symmetric monoidal. But also, it will be generated by objects that are dualizable. So even though not everything is dualizable, it's generated as a category by objects that are dualizable. And then finally, your unit object is small or compact. So if we have a Grothendieck category, the symmetric monoidal, and generated by a set of rigid objects, I use the word rigid and dualizable interchangeably. Okay, they're the same.
So generated in the ind sense. Yeah.
So generated just means that hom out of the generator is faithful. And compact, so that's what this means. And compact means that, so X is compact if homs out of it respect filtered colimits. So this is a notion of smallness. Okay. And as I said, all of those categories that we know and love, like quasi-coherent sheaves on a scheme, will satisfy that. Okay, so another example is if we start with a tensor category, and again, this is here in the classical Deligne sense, and we look at the incompletion, you certainly get one of these. So in that case, the compact object will just be T. Or you could just start with a ring and look at R mod. It's another example.
So what are compact objects in category of quasi-coherent sheaves.
So what are the compact objects here?
Yes.
So finally presented.
From the theorem, yeah.
Finally presented.
Yeah. So, so in particular, if your ring R is not coherent, then the compact objects might no longer be an abelian subcategory. And rigid objects here will be the free ones.
Same, it's not an abelian.
Okay.
You don't care if the compact objects are abelian subcategory.
Sorry?
In your setting, you don't care if the compact objects are abelian.
No, and in fact, that's exactly the case where it gets interesting. Yeah. Okay, so let's go back here. So now we understand the right-hand side. And here are some examples already. Except here I'm lying a little bit, because if I start off with a scheme, it's not necessarily true that the rigid objects will generate the whole category. If I start with a stack, same thing. So I should really make precise what I mean with the left-hand side. Oh. And I have some kind of weird heuristic to try and explain how affine group schemes and stack all relate to each other. I don't know if it will be helpful. Feel free to let me know after. So, okay, let's start with an affine group scheme. As I said, we can think of this as a functor from algebras over k algebras to groups. And we can think of a group as a one-object category, so some point with a bunch of morphisms, isomorphisms. If we take the functor of points perspective, we often think of a scheme as a functor on k algebras to sets. And a set, in this case, is just, if you think of it as a category, it could just be objects, and the only morphisms are the identity morphisms. So now we basically just have objects, where here we only have morphisms. And of course, we need some extra conditions for it to be a scheme, which give you the geometry. Now, a stack, in my sense of the word here, is going to be a functor from k algebras to groupoids. So now we allow multiple objects, and all of them come, or some of them might come with isomorphisms. And of course, we have some extra conditions, some gluing condition, very similar to a scheme one, that actually turns it into a stack. Okay. So what is a stack, or more precisely, what is an algebraic stack? So the way we're going to want to think about it for the purpose of this talk is as a functor from k algebras to groupoids, which is represented by a pair A comma gamma. So what does it mean to be represented by a pair? Well, we have a groupoid on the right-hand side. And so given a k algebra B, I want this groupoid to have objects, morphisms from A into B, and morphisms from gamma into B. So A gives you the objects of your groupoid, and gamma gives you the morphisms. Okay. So given that, I'm going to have some extra structure on my A and my gamma in order to get this groupoid structure, right? For instance, given a morphism, I should be able to find the source and the terminus. I should be able to compose morphisms. Since they're all isomorphisms, I should be able to invert them, and so on. So that gives me some structure on this pair A gamma. So by the unital lemma, the source map is given by a morphism from A to gamma, the target as well. The composition gives me a map from gamma to gamma tensor over A gamma. And here, we think of gamma having left module structure, A module structure via S, and right A module structure via T. And so here, A is working from the left and the right. for every object, we have an identity map on that object. So that gives us this morphism. And we also have inverses. And so given such a structure on a pair A gamma, this is what we call a Hopf algebroid. So in the same way that Hopf algebras are in some sense equivalent to affine group schemes, the Hopf algebroids are equivalent to, in some way that I'll make a little bit more precise, to these categories fibered and groupoids. Okay. A little bit more of a classical definition of an algebraic stack is that it's a stack with an affine diagonal, so in particular representable an affine diagonal, and such that there exists some affine scheme and a faithfully flat morphism from that affine scheme to X. So for instance, if you use this terminology, then an Artin stack would be an algebraic stack, but here we want this morphism to be smooth. But for me, an algebraically stack, we just need faithfully flat. Okay. Then, using this terminology, in some sense, algebraic stacks is equivalent to flat Hopf algebroids. And by flat Hopf algebroids, I just mean that S is a flat map, which is equivalent to T being a flat map. Okay.
So these stacks are kind of affine, yes? I mean,
Sorry?
you only consider affine stacks, not projective spaces.
You don't consider sheaves of groupoids, just groupoids.
For now, I'm just talking about groupoids. And yes, so both A and gamma will be affine, but their representations might be the sheaves on a scheme, right? Because yeah, okay, yeah. So my Hopf algebroids will be A comma gamma, where both A and gamma are commutative rings.
Yes, I think my question is if I can consider something like projective space, is it stack in this sense or not?
Yes.
It is.
Yeah. This is a generalization. This has all schemes in it. So maybe I'll make that clear. Maybe I'll do an example soon. And yeah. And here, I said in some sense equivalence because this is an algebraic stack where you actually choose your presentation U to X. And maybe this is to answer the question. Say I have a stack. So in particular, say I have some scheme. So some scheme or some stack X. I can take a representation. So that means a faithfully flat map from an affine scheme, so from some ring. Then I can look at the pair U. So in particular, this is a K algebra. And I can look at this. So this is a fiber product. You can show if it's an algebraic stack that this is again an affine scheme, and then this pair is going to be a flat Hopf algebroid.
X is like your base in this picture.
So X is a stack, and U to X is some representation of a stack that we choose. So for instance, if you start. No. Yes, you should. Sorry.
So U is like a fine open color. Yes?
Yeah, it's like a chart of
Exactly. So if you start off with a scheme, then you can cover it by, for instance, your open affines. Yeah? And then this will give you your A, and then the way that you glue them together will give you gamma. Does that help? Okay. So, okay. Finally, I want the quasi-coherent sheaves over it to be a Grothendieck tensor category, right? So I want there to be enough rigid objects. And so I should add some extra conditions on my algebraic stack. So algebraic topologists have thought a lot about these types of stacks, in particular atoms, so they're often called atom stacks. So an atom stack is an algebraic stack which satisfies a strong resolution property, which means that dualizable sheaves generate the category of quasi-coherent sheaves on X. So in other words, in our words, your stack is an atom stack if quasi-coherent sheaves on it are a Grothendieck tensor category. Let's do some examples. So if G is an affine group scheme, then this will give you an atom stack. So if you want, you can think of this as a Hopf algebroid given by K, Kg. So that's the Hopf algebroid. Or if you start with a quasi-compact, quasi-separated scheme with a strong resolution property, then you get an atom stack as well. So for those of you that know about the resolution property, so schemes with, or stacks with the resolution property were described by Bertrataro, but it's very complicated and there's still a lot of open questions. But the idea is that most schemes that we work with will have the resolution property. The strong resolution property is a little bit stronger, but both definitions are equivalent for coherent schemes. So in particular, if you have a Noetherian scheme that is separated and regular, then you will have an atom stack. But this is much stronger than you need. So for instance, regular is definitely not necessary.
Is quasi-affine enough?
Quasi-affine is enough, yeah. Because then one will be a generator.
So quasi-projective, I guess, would be the more stable.
Quasi-projective will also be enough, yeah. Okay. A very famous example is a modular stack of formal groups. Or if there are any people here that like ring spectra, so the Hopf algebroids turn up a lot in ring spectra. In particular, if you take some ring spectrum R, then you can look at this Hopf algebroid. And in many interesting cases, this will give you an atom stack. So in particular, for these ring spectra and many more. Okay. Any questions before I go on?
So why did you say regular here? You said that it's not necessary, but why did you include this condition?
Well, because for instance, if I take it out, not every Noetherian separated scheme will have the strong resolution property. So it is enough to be regular, but not necessary.
But if you have something like singular algebraic variety or algebraically closed fields, then it's okay, or certain type
so
of
it's not even known that all varieties have the resolution property. So they definitely don't all have the strong resolution property. But yeah, so it's a very.
Did you say any quasi-affine or any quasi-projective, even if it's singular?
Every quasi-affine variety is generated by, the sheaves are generated by one unit object, so definitely those are fine.
So it's not a question of singularity.
No.
Well, it may be in this generality, but it's not.
So quasi-projective would cover like everything that you want.
I don't know.
Well, let me know. Okay.
Yeah, quasi-affine or quasi-projective will be enough. Something that what might fail is say.
That's what I feel. He's just asked the question. You have to go to the machine.
Oh, what do I have to
You
do?
need to, we can hear Rafael. You're okay.
Rafael?
We should hear.
He probably
Yeah,
can. There he is. He's up here.
Is that the condition of what Kontsevich, Bandal, was it Van den Berg? So in which case it would work in the quasi-compact and separated case?
So
Or is it
it's
different?
Quasi-compact separated is not enough.
Okay, so that's different from what
Oh,
Van and Vandenberg.
actually, I thought that was actually it might be enough. I thought that was open. So, do you think that?
Okay, so maybe it's conjecture.
It is open. It's proven.
Yeah, I think it's true.
Okay, I thought that was still open, but it might be proven by now.
Yeah.
Yeah. Okay.
Like not always open, some others.
Okay.
So this is not a local property. This having strong.
No, it's not. So yeah, what I started writing here was just an example. So if you take a fine space and you do this classical thing where you make it non-separated, then this will be an example where you don't have the strong resolution property. Yeah. Okay.
Even though locally,
Sorry?
locally it has strong resolution.
Yes. Okay. So again, let's look at this. So I've replaced my left-hand side by just atom stacks. And so now the reason that we are restricting to that domain and codomain is because there is this theorem that says that in that case, this embedding is actually full faithful. So Lurie considered a slightly bigger category here. He considered all Artin stacks and then described what kind of morphisms you can get in the image. And then these people here showed that for atom stacks, all of those morphisms satisfy the property. So together they showed that this functor is full and faithful when restricted to atom stacks. And so again, there's a natural question, what will be the image? So recognition was done by Shapi, who showed that C is sheaves on some stack, X, and here, when I say stack, I always mean atom stack. Even if and only if there is some fiber functor to R mod, where R is some K-algebra. And here, fiber functor means not only that it's faithful and exact, but also it should respect coproducts in C.
This is like coming from the flat cover from you.
If you start off with a scheme, yeah, or yeah, for instance, you can take that. Yeah, exactly. If you start off with a scheme or a SAC, you take your faithfully flat cover, then you can take that to be R. Yeah. And you're just forgetting the way you glued things together. Description was mostly done by Shapi, but we simplified the conditions a little bit. So here is C's quasi-coherent sheaves on some atom stack, if and only if for every dualizable object in C. So here I wrote CD to mean all the dualizable objects in C. High enough exterior powers of X should disappear. So that's not unexpected. And X should be locally faithful. So this is a new condition. And this here, you can take to mean that the evaluation map to the unit object should be, the image should be a direct summation of one. So it should split in some sense. So image of this map is a direct summation of one. Okay. So again, it's not hard to show that this is necessary, but it's also sufficient. So now, what about, so we just did characteristic 0, what about characteristic P? So as expected, it gets a lot more complicated, and I'm not even sure if it makes sense to go over all of these one by one, because it's a lot. But maybe, so locally faithful, we just explained. In characteristic 0, it's clear that the symmetric powers and divided powers will still be rigid, but this is not necessarily true anymore in characteristic P. So we need to assume that. And then we want to look at the Frobenius powers of x and x dual. And these should still be dualizable. And in fact, these should be dual to each other. High enough exterior powers to disappear. And then there is some version of Kevin's condition, but we need a little bit stronger. We need to still hold, even when we're tensoring with some dualizable object y. So given those 5 conditions, your Grothendieck tensor category will be quasi-coherent sheaves on an atom stack. Some of these are definitely necessary, but they might imply each other. It's possible that there is some simpler list of conditions, but this is what we have.
What does an x is flat mean?
It means that tensoring with it will be an exact functor.
Are there super versions of such theorems?
Yes, there are, which if there's time, I might, yeah. So, yeah, if there's time at the end, I'll do it. And maybe one day it will be on the archive. Yes.
It seems like a lot of conditions. Are you aware of any sort of implications between the conditions?
Yeah, no, so that's, what I just said is that there might be, but we're not sure. We could, one would hope, but yeah.
Whether it could be replaced by a simpler list.
Sorry?
You don't know whether it could be replaced by some simpler list.
No, we don't know. Yeah. Yeah. Okay. So in the last 5 minutes, I wanted to talk a little bit about reconstruction. So let's do reconstruction first in a more classical case. So we're just looking at a functor from C to R modules, a fiber functor. So in particular, we know that C is going to be quasi-coherent sheaves on some atom stack, or in other words, co-modules over some hop algebroid. But how can I create that hop algebroid? So again, we're going to look at omega x, tensor omega x dual. And then we're going to take the coproduct, this weird coproduct, this co-end construction, where x goes over all dualizable objects in C. Then you can show that this, in fact, has a hop algebroid structure. So the pair here is R comma gamma. And if we look at comodules over that hop algebroid, we get C. So this is a way to reconstruct your atom stack from your category, together with the fiber functor. Okay.
Is fiber functor unique in this case?
No, not necessarily.
Is it known what is how many, like what is the set of all equivalent classes of fiber functor?
I don't know. But you could, if you, I mean, even if R is a field but not algebraically closed, it will not be unique, right?
Yeah, you might have different points.
Yeah, but you can describe.
Yeah, so in general, I don't know. Yeah. Good question, though.
Another question. So do R and gamma depend on your fiber functor, or are they independent of it?
Sorry?
Do R and gamma depend on the fiber functor, or are they independent?
Oh, so good question. So R already appears in the fiber functor, right? But here you're making a choice. Given some stack, there might be different presentations. And so given the stack, that this fiber functor will not be unique. There might be a second fiber functor to some other R prime mod, and then you will get some other Hopf-algebroid R prime, gamma prime, that gives you the same category. So certainly, yes, the fiber functor gives you R, and then from there you build gamma, but it's not inherent to the stack. There's many choices. Yeah.
And would these be like isomorphic as Hopf-algebroids, or who knows?
So depends on, there's different, there's like a notion of weak equivalence. They will be weakly equivalent. Yeah. Okay. So slightly more general. Instead of looking at fiber functors from C to R modules, I want to replace K modules by the category D. So I'm going to start off with some Grothendieck tensor category. We can take a coproduct, D with D, which I haven't defined, but which I'm sure you have some idea of what it would look like. And there's a canonical map to D, so which should be the identity on both factors. So suppose that this functor here is exact and faithful, which will not always be the case. For instance, it will not be the case for R modules if R is some ring, usually. But it will be the case, for instance, for vector spaces, for supervector spaces, and many interesting tensor categories. So if this map is exact and faithful, and we have a fiber functor from C to A modules in D, where A is some commutative ring in D. Then we would like to write C as comodules over some Hopf algebra in D. And so we can do this construction. Again, we build a co-end. So this will now be an element in D, and you get a left A module structure via this factor and a right A module structure via this factor. Together, A and gamma will form a Hopf-algebroid in D.
So the example to keep in mind is D is some sort of incompressible category, let's say verp E or verp E to the n.
Yes.
Or superspaces, which is what they asked.
Yes. So in that case, what do we get for reconstruction? So it's a little bit different than before, but the idea is, so we have our comodules over the Hopf-algebroid together with a forgetful functor, where we forget the action by gamma, so we just get A modules over D. We have this functor, which C to dA is the original functor we started off with, and we can extend scalars. So we get a functor like that. There is some canonical functor such that this here commutes, and then we can show that this here will be an equivalence. So we can build C coproduct D as comodules in D. But then how can we recognize C in here? So I won't have time to define it, but there is some full subcategory in here, which is where the action by the fundamental group of D agrees with something here. Okay, so some full subcategory here that is explicitly described will give you C. So you don't get C as comodules over D, but you get it as some subcategory of comodules. which if you've done Tannakian theory for, say, supervector spaces, should look very familiar. Okay, so this will be an equivalence. Okay. And then I'll end with a little application. So the two category of Grothendieck tensor categories has all finite coproducts. And in fact, if I have two atom stacks x and y, I can form their fiber product, which will give me an atom stack, and look at the Grothendieck tensor category that I get from there. Or I can take the coproduct of sheaves on x and sheaves on y. And you can show that these two will be equivalent.
This is a Deligne product?
Well, Deligne was for tensor categories. So it will be this will be the incompletion of the Deligne product, yeah.
So here you assume that field is algebraically closed.
Sorry?
So field is algebraically closed, or it is perfect?
No, K could be any ring.
Ah, any ring?
Yeah. So this is actually the product of defined in general for Grothendieck categories. And then you can show that this will also give you a coproduct of Grothendieck tensor categories. And yeah, so in particular, if you take x and y to be quasi-compact, quasi-separated schemes with the resolution property, this will work.
Sorry, is that different than the kind of Kelly tensor product? There's this representable
No.
tensor product of like
It's the same as Kelly product.
So it's like a completion under most colimits?
Cool.
You take you take the naive product and then you complete it under.
Yes. So yeah, it is a complete, like it is a, if you have generators here and you have generators here, you look at all pre-sheaves on it, and then you take some subcategory. So it's some type of completion. Yeah. So I'll stop here.